my name is Forrest Glines. I'm a graduate student at Michigan State University working with Brian O'Shea and Philip Greta. So I'm one of the 2019 Blue Waters Fellowships. So one of the advantages of my talk is that I don't have to show any results because I've just started on Blue Waters and I can claim ignorance and everything else. But anyway, so what I'm doing with Blue Waters is I am using Blue Waters to study astrophysical magnetized turbulence in galaxy clusters in preparation for next generation isolated galaxy cluster and cosmology simulations using this performance portable MHD code K-Athena that we've developed at MSU. So before we get into that though, so first, why are we interested in magnetic fields in plasmas? So magnetized plasmas are ubiquitous in the universe. They describe many different phenomena from stars to black holes and play a role in the evolution of galaxy clusters and galaxies. For example, this is an all-sky map of the magnetic fields that we can see here from Earth, as seen by Planck. And it's mostly all just the magnetic fields within our own Milky Way. You can see that the magnetic fields have interesting interactions with the baryons in the disk and the overdense baryonic regions where there's lots of star formation generating magnetic fields. Particularly though, we are interested in the magnetic fields within galaxy clusters, which are the largest gravitationally bound structures in the universe. It's these groups of galaxies that are 90% in mass, dark matter, and of that leftover 10%, 90% of that baryonic matter is in this diffuse intracluster medium seen in purple and X-ray here in cluster Abell 2744. So we know that these galaxy clusters have strong magnetic fields due to the abundance of synchrotron radiation emission that we see in radio in red in this image. So the synchrotron radiation, it comes from relativistic charged particles breaking within magnetic fields. So wherever there's synchrotron radiation, there must be strong magnetic fields. Incidentally, these charged relativistic particles, these cosmic rays, are streaming along these magnetic fields, and they affect the overall evolution of the galaxy cluster as well, introducing extra anisotropic pressures. They prevent mixing, they can inhibit turbulence, and all kind of interesting fun effects that we would have to simulate in a full galaxy cluster simulation. How exactly these galaxy clusters got these magnetic fields as strong as they are right now is a little bit unknown. There are numerous theories, but there are numerous different mechanisms to introduce magnetic fields into the galaxy. For one, there's the active galactic nuclei. These are the supermassive black holes at the center of galaxy clusters. And although they're very small objects, maybe evolving on the scale of 1 AU, they're able to dump out energy to tens to hundreds of kiloparsecs in the galaxy cluster, contributing to its quasi-stability and preventing many galaxy clusters from going what's known as a cooling catastrophe. So as these AGNs at the center of the galaxy cluster, as they accrete mass, they dump out energy, they heat up the cluster, they're also spitting out a lot of magnetic fields, which in turn can build up into larger magnetic fields and affect the structure of the galaxy. Additionally, there's a lot of turbulence in these galaxy clusters. So for example, this is a galaxy cluster simulation from the Matryoshka simulations. So it's just a very zoomed in piece of a galaxy cluster, and illustrating the vorticities in the turbulence. And the magnetic fields that are within these galaxy clusters, they interact with this turbulence through introducing what's known as the small-scale dynamo effect, where as the kinetic motions in the turbulence sort of they twist and wind up these magnetic fields, amplifying the magnetic fields that is already there, and possibly accounting for the strong magnetic fields that we see in these clusters today. So each of these secondary effects with magnetic fields, they are increasingly becoming more necessary for next generation galaxy cluster simulations and next generation cosmology simulations. And each of these additional effects, and as well as increasing the grid resolution, they increase a high computational cost. such that to go to the next simulations will require the next generation of machines and the next generation of architectures. However, one of the issues with all these next generation exascale systems is that for the most part, our old C++ and Fortran codes, they don't work on these new systems because they're all using weird accelerator GPU-like architectures. So for example, just looking at sort of the current generation and these next upcoming computers, of the future, the 4 computers that are being built, only Frontera is going to use sort of your typical Skylake CPUs. Now the other ones, Perlmutter is using NVIDIA GPUs, Aurora is using probably using some Intel GPU, which they haven't quite announced yet, and Frontier is using AMD GPUs, which I guess I wasn't thinking of programming for. So the issue with this is that all these different accelerators, they each have their own API. And so if we wanted to rewrite our code using their APIs, that would be another rewrite for every single simulation, every single machine. And if the next machines are something like FPGAs, or if it's an ARM thing, we'd have to rewrite it again. So one of the goals, I guess, in computing, and one of the things that we've been interested in are the development of what are called performance portable codes. So these are codes that can run on any machine at high performance with a single code base. There are a couple of tools to help you do this. First, there was OpenCL. It works, it's gold standard. It's a bit of a pain to write in, though, and it's becoming deprecated and folded into Vulkan. So it's not a really good idea to go with. There's also OpenMP and OpenACC, which are very good long-term solutions, but they're also very compiler dependent. Mostly the IBM compilers are far and ahead with these, but anywhere else it's difficult to get the same performance and features as you could get with CUDA. So next, though, what we're interested in were these, could sort of call them abstraction layers, these C++ libraries, Oka, Raja, ooh, that got cut off, and Cocos. And what these do is they wrap your kernel within a function and then compile it to the target architecture as you need it. So it could compile your Lambda, your kernel for OpenMP, for CUDA, for pthreads, for AMD ROCm, whatever you need. So when we first looked at writing such a code, we saw that Cocos was the best suited for what we wanted due to its options in managing memory. So we went ahead and developed a code. We took the existing Athena++ astrophysical MHD, it's a finite volume plasma code, and we converted it to run on GPUs and CPUs using the Cocos performance portability library. And this actually turned out to be a lot easier than we were expecting. It was only about 300 person hours between myself and Philip, working from July to December of last year, in between of a ton of different other projects that we had. And we were able to get something running really fast on GPUs while maintaining most of the performance on CPUs. And so there's a paper that's submitted, and you can go look at the code right now. It's open source, it's up on GitLab. What did this conversion look like, though? So this is, so on the right we have what the original Athena++ code looked like. It's a bunch of triple for loops with some SIMD pragma statements to get that vectorization. And all we did was convert the loop statement, convert the loop body into a lambda function, while pretty much we didn't have to touch anything else within the lambda, within the loop body, just change that heading to the Cocos lambda, and convert the loop structure from our triple for loop to a Cocos parallel for, where that MD range policy is a Cocos data structure that defines our loop bounds. And after doing this, we had something that ran on both GPUs and CPUs. Cocos also gave us a lot of flexibility in how we wanted to make that change, just going from that flat basic parallelism that I showed right there to something more complex where it exposes the hierarchy of, on CPUs, it might be your cores, your vector thread, your SIMD vector threads, and equivalently on your GPUs, your CUDA blocks and your warps. So with Cocos, you have the flexibility to target both of these architectures and optimize for both simultaneously. So we did this to the whole code. It turned out to not be too many kernels, and we also updated every data structure to be a COCOS data structure so that it could transparently access memory on both the CPUs and the GPUs. And it worked really well. So here's K-Athena's performance compared to state-of-the-art codes on just a single GPU and a single CPU. So on the right, this is a number of cell updates per second versus the problem size. And comparing it to Gamer on the Pascal GPUs, which is comparable MHD code, we were actually able to outperform them by just a little bit. And on the Voltas, we're performing upwards of 100 million cell updates per second on a single GPU. And looking back at the CPU side and comparing it to the original Athena++ CPU-only code, we only lost a couple percentage in performance compared to their solution. But in the end, we had a code that was much more flexible in its level of granularity in parallelization. Looking at how it scaled, though, we took K-Athena to a number of different systems from, we have NASA Pleiades on the Electro nodes down to Summit Volta GPUs. And looking at the performance of the C code, we maintained mostly the same constant performance scaling as the original Athena++, maintaining 80% parallel efficiency to thousands of Skylake nodes and thousands of Knight's Landing codes. Moving over to Summit, though, we were able to do a run with over 4,000 GPU nodes using 24,000 GPUs, and we were able to obtain over 2 trillion cell updates per second with our code. And we were getting to the point where just the sheer number of MPI messages were degrading our performance. So now that we had this performance portable code, we asked ourselves, what did we want to do with it? Eventually, we wanted to do multi-physics, but we wanted to look at something quick that we could do. And we decided to do some magnetized turbulence runs. So for example, this is some driven turbulence simulations that were done previously. So where this is the full box, the full simulation, and this is decomposed into different energy spectra. What we wanted to study was the energy cascade, or the turbulent cascade, which is this relationship where large-scale driven flows decay into large-scale eddies, which these turbulent eddies break down into smaller scale turbulent eddies down until it gets to a viscous length scale. Now the issue in simulations is that the resolution range between this large scale and this viscous length scale is far too large for any feasibly constructed computer to resolve. So our goal was to resolve at least part of this energy spectrum so that we can resolve at least part of this inertial subrange and compute a slope for the compressible magnetized turbulence for our particular interests. And so, yes, with the extra wrinkle that the small scale turbulent dynamo in this magnetized turbulence will affect the typical slope that you would see in ideal hydrodynamic simulation. So particularly what we're using, though, is what's known as the Taylor-Green vortex. And this was because of some previous work that we did done by the group that found that these driven turbulent simulations were introducing some bias in the results. So this is it's pretty much a sinusoidal pressure and magnetic field that formally decays into a chaotic turbulent flow. And so once we're done simulating this for a couple of dynamic times for a few different parameter ranges, we'll be able to develop subgrid turbulence models that we can insert into full multi-physics simulations of isolated galaxy clusters using K-Athena. So this is what we hope to get to with our work with Blue Waters. It might just remain in the development phase if So we're limited to December. And the long-term goal, though, is to bring the same kind of work into Enzo-E, which I think we'll be hearing about very soon. So if there are any other questions, there's a link to K-Athena right there.